Okay. Yeah, I know. Newton's laws of motion. The first law. An object at rest remains at rest and an object in motion remains in motion. At a constant speed, in a straight line, unless acted on by an unbalanced force. God bless you. Does anybody know the other name that they have for this law?
Miss Rose.
Yes, ma'am.
Hey, Brian Kraft, could you please admit him? He left out before grabbing the note.
Yes.
Okay, thanks.
Okay, my question was, do y'all know what they call this? Yeah, they're all the laws of motion. The first law that says an object at rest stays at rest, an object in motion stays in motion. They have another name that they give this. Do you know what it is? No. Okay. Y'all don't know. That's okay. Now you're going to learn. This is also called the law of inertia. The law of inertia. I'm going in red. Trying to stick with the apple theme. And you can like color and doodle and whatever. That's for homework. And you've got to study these laws. Like you got to know these. And understand them and what are they saying. Okay? So let's break this down. The book is at rest on the table. True? It's going to stay that way until okay, here's where most people have the misconception. It's not just any force that goes on it. Because remember how we talked the other day and I took the book and I kind of pushed it but it didn't go anywhere? Like right now, I'm putting a force on my paper. Oh, I barely moved it. But I'm putting a force on my paper that way. But it's not going anywhere. It has to be an unbalanced force. Remember from our other notes, see this keeps building. From our other notes we learned unbalanced forces cause acceleration. Okay? So in this case, it's going to stay at rest. Not just until I put a force on it, until I put an unbalanced force. Okay? Yes. That wasn't from yesterday. We took notes and they're on the computer. Okay? Okay. The other part of that is an object in motion stays in motion. So if I'm moving, I'm going to continue to move in a straight line at a constant speed until an unbalanced force acts on me. Okay? That part's a little bit harder to understand because we are so used to unbalanced forces. Like we know friction. We know gravity. You know, like, according to this law, if I pick you up and throw you, guess what you're going to do? You're going to go at a constant speed in a straight line for infinity. Like just go. You're just going to... So if you throw a football, see, a football doesn't actually go in a straight line. It's a curved path because of gravity. But according to this law, if there was no gravity, gravity's the unbalanced force. You see what I'm saying? Like if I took you and threw you, you would just keep going in a straight line at a constant speed. Forever and ever and ever. Infinity. Yeah. Does that make sense? Unless something stops it. Yeah. Like if we were in space and we had this lid to my water bottle, and we threw it, it would just keep on going until something came in contact with it that gave it an unbalanced force. It wouldn't fall in space. An asteroid. He says an asteroid would hit it. But y'all, if we didn't have gravity, this same thing would happen on Earth. That's what I'm trying to tell you. So if we didn't have gravity, when I threw you, you would just keep going. Okay, but gravity is here, so you would fall to the ground. Does that make sense? Everybody understand what I'm saying? Any questions on Law 1? Okay, awesome. Law 2. Well, it's still there, and it's on the sideboard as well. Acceleration of an object depends on the mass of the object and how much force is applied. Okay, the other thing that they named this is we're not going to learn equals in two squared. F is, what's F? What's capital F? Force. What's little m? Mass. And little a? Acceleration. Okay? So, this is the one I like to say. This is what I like to call it. This law is your grocery cart at the beginning of your shopping trip versus the end. Don't say heavy. Here's your cart. This is why you don't say heavy. What does this law deal with? Mass. And what is mass? No.
How much is the object weight?
No! Mass is not weight. That was one of the first lessons I taught you. The particles inside of it. That's your mass. Look at my shopping cart at the beginning. How many particles? You see what I'm saying? But at the end, I put all kind of stuff in my basket so I get more mass. And what am I going to need to make this with more mass accelerate? What? But could it be the same force as when it was empty? If the mass goes up, the force has to go up. Does that make sense? That's this right here. Okay? So anytime they're comparing sizes of objects, it is a dead giveaway. I never understand why kids get the second law wrong. Because the second law is the easiest one. They're going to talk about this guy being big and this guy being small and whatever they're doing. You see what I'm saying? They're going to compare sizes most of the time, comparing sizes of objects because it's talking about mass and how much force you're going to need to make it speed up or slow down. Okay? Third law. If one object exerts a force onto a second object, the second object exerts an equal force in the opposite direction back onto the first. Well, yes, you are right. It is going to deal with something with balanced forces because the arrows need to be the same size. But what's going to be the catch? Opposite direction. Okay, so yes, when you have to draw for this law, your arrows are going to be the same size. They're going to have to be in the opposite direction. The other thing they call this is the action-reaction law. And I know that seems so much easier, but sometimes if you don't understand where the forces are coming from, it is so hard to label them. Okay, so let's say I take my hand and I'm object 1. I put a force onto a second object. The second object puts an equal force in the opposite direction back on here. So that's why if you would punch the wall, you'd break your hand. Does that make sense? Or you slap your brother and he runs off crying, but your hand hurts. Guess what? He slapped you back. Yes, he did. Yes, he did. He slapped you back.
I'm going to use that.
See what I'm saying? When you put a force onto them, they put a force with the same amount in the opposite direction back onto you.
I can use that excuse. He hit me back.
He hit me back. Did y'all get it?
Yeah.
So this is usually like, actually, y'all, law 3 is how we walk.
Or it's like when you give somebody a high five. Yeah, our feet would go through.
No, not go through. Like, yeah, it would, yes. Okay, awesome. Good job. Here we go. I thought I had a different... Some of the colors, it doesn't matter what you use, okay? And not everything we're going to color in. I'm using pink right now. I know y'all don't have pink. Or if you do, great, I don't care. If just don't use orange, because that's for gravity. Okay, inertia is, they say it as the resistance of motion. Here's what I'm going to write. I put resistance of motion, but I want to put a little something else right here. Objects want to stay in their state of motion. Sorry, that's hard to see. So, inertia is, doesn't matter what object you have, every object wants to keep doing whatever they're doing. If you're running, you want to keep running. That's why it's hard to slow down.
Also, like for a car, when it slows down, it doesn't really slow down.
No, okay, let's relate it. Since you brought up a car, let's talk about a car, okay? So everybody imagine you're in the car with your mom or whoever, okay? And they take off. And what do? Because I want to stay where I was. So our body does like this because we were there and the car's going that way. Our body wants to stay there. See what I'm saying? So then when they apply the brakes, you do this. You go forward because you want to continue moving like you were. Y'all were going forward in the car. So your body wants to keep going forward. Does that make sense?
Yeah.
And see, you will keep going forward because who gets the unbalanced force? No. The car. Do you have brakes? No. Humans do not have brakes.
They have to stop themselves.
So the car gets the unbalanced force and it goes to stop. It doesn't want to, but it does go to stop. You need a good force to do it, right? But you don't have brakes, so you go forward. That's why we have to wear seatbelts. Okay? And according to Newton's laws, when you fly out the car from not wearing your seatbelt, you're going to keep going at a constant speed in a straight line. And if there was no gravity, you'd keep flying like that for eternity. Unless you hit something, like the tree. Right? Y'all get what okay. Does that help? Do y'all understand what it means, breaking it down? Okay, so inertia is we don't want to change our motion. Yes, sir.
This is like the average question, but does it have to do with you getting car sick, like when the seatbelt pushes you?
No.
I was just saying.
Sorry. This resistance in their change of motion is including changes to speed, direction, or state of rest. So they're just saying they don't want to change their speed, direction, or state of rest. Like if you're at rest, you don't want to move. It's actually harder to get something to move than to keep it moving because of inertia. I didn't hear you. I'm sorry, Janie. Exactly. Did y'all hear what she said? Makes sense. Yes.
Like on a bike. Say you're on a bike and you stop. Before you keep that bike. What would happen?
You are going to go forward. Some of you is going to accelerate forward because you were already going forward and the brakes were put on the car and not on you.
I'm talking about like a bike.
It does. I mean, on the bike, it's the same thing. Like you put your brakes on, you know, say they're here. You grab the brakes, you're still gonna go. Okay.
Never. If you're riding a bike and you have like the front brakes too, like and you only use front brakes, you're gonna go forward. Because then the back picks up. But then when you put back.
You know, like in the movies where they're like riding on the horse and they're going through the forest and all of a sudden the rider's not paying attention and the tree hits him, but the horse keeps going?
Yeah.
That's it. I mean, because I don't know how else to explain it to you besides all of those are examples. You got the unbalanced force, the horse didn't, so the horse keeps on moving, but you got stuck by that tree. That's it. An object in motion. Y'all tell me the words. Okay, stays or remains, yeah. With the same speed and in the same direction unless acted on by unbalanced force. I don't know. Okay, here we go. This arrow is your force, right? What force, that's purple, what force is acting on the ball? Okay, are there any other forces acting on the ball? Gravity. And I heard somebody? Normal force. Okay, so orange is going to be gravity. Can I just, like, abbreviate? Let's put the blue color is the normal force. We're going to use a green color for friction. Yeah, because I was saving it for right now, boo. Don't be clowning me. And there's going to be some friction like this. But it's small, right? Because he's going to accelerate. Yeah. The force causes the ball to roll what? Down the ramp. And it's the purple one causes it. I'm going to put that in purple like that because it's the purple force that causes him to do that. Yes, sir.
That's the credit last night. The new one you put down. Is it on 5 pages?
Yeah. There's a bunch of pictures and graphs on it. It's not like, 25 questions a page. You know what I'm saying? Okay. Next. What do we have here? We're going to put a force on the ball. There's what? There's a lot of friction. We're going to have to overcome friction. But he's going to roll up, right? So what size does it need to be? Big or small? No, small. Because we're still going to accelerate. Tell me, what are you talking about? Because this is what you're going to have to draw on the experiment.
How would it not be a lot? You have to overcome friction to get up there.
I am going to make it go up. He is going to go up the ramp. Okay? To make it go up the ramp,
You have to apply.
my force, this original force, is got to be bigger than friction.
Oh, okay.
So I drew him smaller than that.
So okay.
I still have gravity acting down, and the normal force is perpendicular to the surface, but he's the same size as gravity. Tell me?
So you have to give a greater push than friction?
If I push equal to friction, two forces the same amount are balanced. What makes something actually move? An unbalanced force. So that's why we're drawing all this. The vectors are there. Gravity and friction act against the force of the ball, on the ball. Does that make sense? Okay, what about the last one? Okay. What else, though, does it have to be so that the ball will never stop? No friction. Okay, that is called frictionless. So I still have gravity.
So it seems like the ball is rolling on ice.
Yeah. Yeah, but, you know, our ice is still going to have those little hills and valleys. Yeah. So in a frictionless surface, it would be if we could make the ice a perfect straight line across. Yeah. Okay, are we good? Awesome. Oh, yeah, the ball will never stop moving. Okay, what do we have here? Okay, but what forces do we have? Gravity, normal force. Well, I don't really think we have friction if nothing's applied to it right now. What's the motion, though? Y'all, what's the motion right here? At rest. What is going to make it go down right here? Well, obviously something has to give it a force to move it to the edge. But what's going to make it? Yep. So this is orange still because that's gravity. Okay. Now he gets down here. What's gonna make them go up right there? What's gonna keep them moving? Who? Huh? Good job, Jane. Are you writing? I put it in pink because I used pink earlier. So you'd probably even have some inertia like right here too. Yeah, to get you to that heel. It's okay. It's going to work. Where does it go? Down here? Good job. Gravity. Okay, and then let's say this is the end. What's going to happen right here? Friction. Friction from? Nope. Nope. Good job. So we're going to have a big friction arrow, right? Because we're going to need a good amount. Friction from the brakes gives unbalanced force to what? Yeah, but to do what to the car? Decelerate. So I'm showing you that those unbalanced forces can be accelerate or decelerate. So you see this box right here? That's part of your homework. This one. You could just do it in pencil. Okay? Okay. We're getting there. Almost done. It's almost time. Mass is in purple. The amount of matter in an object. So, how does the mass of these compare? Tell me about their mass. Which one has more particles than the other?
The bigger truck.
This?
Yes. The bigger. Yeah, the huge truck. It's a tractor. Same. One that has wheels. They both have wheels.
It's purple. I'm still using purple for mass on all of the mass part. And which one has the least mass? Okay. How will the mass impact their ability to speed up or slow down?
Because the mass determines how much force is affected on the object. So
Okay. The sports car will speed up faster because it requires the least force to get moving. Who doesn't understand? So acceleration is in some kind of blue. And we're going to give him what kind of arrow? The biggest arrow. Yeah, so we're going to let his go like he is going to, yeah, like, let's see, he's going to have some behind him. Yeah, he's going, okay? He's going to get a fast, or the fastest start, right? What about these two guys? Do they need the same arrow? No. So who gets the middle one? The truck with the logs gets the next one. No, they're going to gain more momentum than you because which one do you want to get hit by? I want to get hit by the car. Okay? So, I want to get hit. Well, I know. Oh my gosh. Nobody wants to get hit by the car, but you have these three choices, genius. You get hit by this because they're going to pack more punch because they've got more mass. But no, they accelerate slower. They're going to catch up. They can get there. They got to work harder for it. They need more force to do it. Does that make sense? I'm still in blue. Let's write what some of that stuff that he was saying. All can go fast, but they all cannot change speed the same due to mass. That's the thing, like, yeah, I could take a big old linebacker and make him be a wide receiver, but he can't accelerate fast. It's not just that he can't take off, it's that he can't take off fast, he can't change direction fast, and I mean, it's okay if it's harder to slow him down, but acceleration is not just speeding up. It's all of them. Speed up, slow down, change direction. So, yeah, this guy, he gets the fastest start.
But they're going to catch up eventually.
But they can catch up eventually. It's just going to take them more force to do it. That's what this says.
It takes a little longer to stop because it's going at a faster speed.
Yeah, it could. Yeah, but they're gonna. No, these are gonna pack momentum. It's gonna be hard to stop them.
Yeah, because it's not quick to stop you. It'd be easier to stop it.
It's easier to stop the car. It takes less force to make a little mass accelerate. And remember, accelerate is speed up, slow down, change direction. So when I talk about it, do not only think I'm saying speed up. Okay? This piece right here is your homework. Okay? So you have the other little piece and this little piece. And then reading your laws, coloring in and doing whatever else, because I still have some of this to color in like I started in my other class.
Do you have to do this like every